Okay, so now that leads very neatly into the fundamental theorem of calculus. So we noticed from 18a, section 18a, we were finding the area under the curve. And the area under the curve, thanks to Sir Isaac Newton, who, by the way, discovered or invented calculus when he was 18. So if you're interested in doing that, you better get a move on it, I suppose. And then there's Gottfried Wilhelm Leibniz, who also worked on the calculus stuff. So between them, they defined the area under the curve as the integral of the function when it's evaluated from a to b. And the integral has great meaning, and we're going to get to that in a few minutes. If we look at this investigation from your textbook on page 450, we take a look first of all at this function y equals 5. Okay, f of x equals 5, it's just a constant, it's a horizontal line. We want to find the area underneath that, below this curve, or this function, between a and t. So these are just two x values that we're going to be using. So x equals a and then x equals t. So using this integral notation, the area in terms of t is the integral from a to t of 5. So we're finding the area under this line, y equals 5, between a and t. Okay? And dx is part of this expression here. So that equals the shaded area under the curve. So the shaded area, well, it's a rectangle. So we can do t minus a, which is this distance right here. So this whole distance here is t, all the way to there, and this distance is a, then t minus a must be this distance right here. And t minus a, well, and we multiply, so it's a rectangle, so we multiply t minus a times the height of this. Well, the height of that is at y equals 5. So t minus a times 5 is the length times width of this rectangle. And if we distribute this 5 in here, we get 5t minus 5a. Okay, so then if we write this a of t in the form of f of t minus f of a, f of t equals 5t, and f of x then would equal 5x. Well, notice what happened when we looked at those last examples for the anti-differentiation. When we increase the value of x, or the power of x, notice here that we end up with 5x where we just started with 5. Well, this 5 here is actually 5x to the power 0. And this 5x down here is 5x to the power 1. So we've added 1 to the exponent of this x, so we actually took the antiderivative to get the expression for the area under this curve. And so if you were to take the derivative of this, you multiply 1 times 5 to get 5, subtract 1 from the exponent to get 0, and you know x to the power 0 is just 1, so that would just leave you with f of x equals 5. Okay, so when you, if you would please continue on in investigation 2, on page 450 of your textbook. One thing to notice, and we looked at this on Monday. I don't want to draw this because I'll probably do a bad job of it. But we have a curve, and maybe I'll just do a quick sketch. So we've got a curve here. It's going through the origin at some angle, like this. And we're trying to find the area between two values like this. Okay, so here's a, there's t. Obviously between the two is t minus a. And we know the height here, well this is y equals x. So if y equals x, then if x is a, then the height of this, that's y equals a here. And if y equals x all along this line, then when x equals t, this point right here, this y value has to be t, so that means the height has to be t. So then what you can do is you can find the area of this shape. So instead of breaking it up into a rectangle and a triangle, what is this shape? Okay, and what's the area? What's the formula for the area of that shape? Okay, so what we can do is we can, I'll just start you off very briefly. We've got the area, which is the integral from a to t of x dx. Okay, and so then we know that that's the shaded area, which is this shape here, this trapezium. Okay. And then the formula for the area of a trapezium is the two parallel sides, t plus a, divided by 2, multiplied by the height between them, which is t minus a. So what I'd like you to do from that point, can you please continue on to determine an expression for f of x. Okay, so I can bring this 1/2 outside. So I have 1/2 t plus a multiplied by t minus a. And if I expand this all together, that's just the difference of squares, so I get t squared minus a squared. And then expand the 1/2 in. So we have to remember that a is just a constant. T is the variable. So if you take the derivative of a constant, it just disappears. Okay? So then the expression then, f of x would just be 1/2 x squared. And then whatever constant that would be. Again, notice that when the original function is x, the exponent here is just 1. The new exponent now is 2, and we had to multiply by 1/2 to get that coefficient of 1 again, if we took the derivative of this. Okay, so again, the area under the curve is giving us the antiderivative. Okay, so just what we found from the last examples through the investigation, that the integral, or the area under the curve, is the same as the capital F of t minus capital F of a. So the antiderivative of the function evaluated at t minus that evaluated at a, where the derivative of that capital F of x is just the function f of x. So that tells us that this capital F of x is the antiderivative of f of x, the original function. So the fundamental theorem of calculus for a continuous function, when we have this continuous function of f of x and the antiderivative of capital F of x, then that integral of f of x dx evaluated from a to b is just capital F of b minus capital F of a. So once you get that antiderivative, then you just evaluate it at the second endpoint, evaluate it at the first endpoint of the interval, and then subtract. Okay, so that gives us the fundamental theorem of calculus. So if you look at page 452 in your textbook, you'll be able to see some properties of definite integrals, which will probably be a good use of about 30 seconds of your time. And so then we'll take a look at a couple examples here before we go. So if we want to find the area between the x-axis and this curve y equals x to the power 4 between x equals 1 and x equals 2, we would need to use this integral. So it's an area. So the integral from 1 to 2 of x to the power 4 dx. Well, what's the antiderivative of x to the power 4? Well, the capital F of x is 1/5 x to the power 5. Right? So if we take the derivative of that, 5 times 1/5 just gives us 1, that coefficient, and we subtract 1 from the exponent to give us 4. Okay, so then we're going to bring this now back over here, and we're going to evaluate f of 2 minus f of 1, and this capital F is this function over here. So we've got 1/5 2 to the power 5 minus 1/5 1 to the power 5, and so 2 to the power 5 is 32, so this is 32/5 minus 1/5, and that gives us 31/5 square units. Sorry, I missed some of that. Okay, so this then is the derivative, or sorry, the integral of x to the power 4, or basically the area under x to the power 4 above the x-axis and between x equals 1 and x equals 2. Okay, so let's do one more example here. So again, now what we need to do is, we know we're trying to find the antiderivative, and we're evaluating it from x equals 2 to x equals 4. So I always like to change this to x to the negative 1/2, just to change it from radical form into exponent form, and then the antiderivative f of x, then, well, we'd have to then add 1 to the exponent. So if we add 1 to negative 1/2, we get 1/2. And so if we were to then take the derivative of this, we bring the 1/2 down in front to multiply by the coefficient and subtract 1 from the exponent, which gives us the negative 1/2, so that's no problem. What do we multiply this half by to get 1 here? So that's the thing. So then we end up seeing that that's 2. Okay, so then the area is the integral from 2 to 4 of x to the negative 1/2 dx, which is f of 4 minus f of 2. So then we just substitute 4 into this, and this is actually capital F. Then we've got 4 to the 1/2 minus 2 times 2 to the 1/2. So it's the same function, this function over here, just with different values substituted in. So the square root of 4 is 2. Square root of 2 is the square root of 2. I'll just leave it like this for now. And so then 2 times 2 is 4, so we get 4 minus 2 root 2. And if you factor out a 2, you get 2 quantity 2 minus root 2 as the area under the curve. So that would be u squared. Okay, so that is about it. So here's a few practice questions for you. So have a little fun with that. Thanks for watching, and we'll see you in class.